Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So imagine roughly 300 million kilometers away from where you're sitting right now.
Yeah, that is a long way.
Right. There is this rock just suspended in the freezing, irradiated vacuum of space. And, I mean, it's not particularly massive in the grand cosmic scheme of things. It's only about 900 meters across.
Small, yeah.
Exactly. It's essentially just this jagged, desolate mountain of black dust and rubble. It's a C-type asteroid known as Ryugu, and it's just endlessly hurtling through the dark.
Hurtling through the dark at tens of thousands of kilometers per hour, actually.
Right, and yet, amidst that completely frozen desolation, scientists have somehow managed to extract the literal fundamental chemical alphabet of biology.
Which is just, it's staggering.
It really is. We are looking at an environment that seems entirely, antithetical to complex chemistry, let alone biology, and we're finding the precise molecular precursors required for existence as we know it.
Yeah, the building blocks.
So, okay, let's unpack this. We are going to figure out how a few pinches of black dust from deep space are completely rewriting our understanding of how life on Earth might have begun.
And we'll also unravel a brand new chemical mystery that, honestly, scientists didn't even know they were looking for.
Yes, exactly. Because the contrast here is just, it's what makes this so incredibly compelling.
Right, because you have this near absolute zero vacuum, right? It's being constantly bombarded by cosmic rays. And yet, trapped right within the lattice of this carbonaceous chondrite are the canonical nucleobases.
Which, for anyone who needs a quick refresher, are the exact components of DNA and RNA.
Yeah. For decades, the lingering question in astrobiology has really been how a volatile, molten early Earth acquired these complex, delicate nitrogenous structures that life actually requires.
Because early Earth was basically a boiling nightmare of lava.
Exactly. It was not a hospitable place for delicate chemistry. So this finding from Ryugu, it provides one of the most complete empirical puzzle pieces we've ever secured. It fundamentally shifts the conversation from just theoretical modeling of prebiotic chemistry to actually analyzing physical, pristine evidence.
And the implications of that shift are just monumental. I promise you, by the end of this conversation, the way you look at the night sky and really the origin of your own cellular makeup is going to completely change.
I completely agree. It really changes your perspective.
But before we can even begin to understand the biology and the chemistry happening at a microscopic level, we have to talk about the physical retrieval of this material.
Oh, the mission itself.
Yeah.
Because the sheer audacity of how these rocks got into our terrestrial laboratories cannot be overstated.
It's an absolute triumph of planetary science. We're talking about the Japanese spacecraft Hayabusa 2.
Right, which blasted off back in 2014.
Yeah, late 2014 from the Tanegashima Space Center. And the engineering here is just... it utilized these highly advanced ion engines, which always sound like something straight out of sci-fi.
They do, yeah. But they work by ionizing xenon gas and basically accelerating it through an electric field. It provides a very continuous, highly efficient thrust. But, this wasn't just a direct point A to point B flight.
No, space travel rarely is.
Right. It required years of precise orbital maneuvers. They had to utilize Earth gravity assist just to match Ryugu's heliocentric orbit.
Which is an incredible feat in itself when you think about it. You're trying to intercept a rock that is less than a kilometer wide.
Moving incredibly fast.
Hundreds of millions of kilometers away. The margin for error is essentially zero.
Yeah, non-existent.
And when Hayabusa 2 finally arrived at Ryugu, which was in the summer of 2018, it didn't just, immediately swoop in, scoop up some dirt, and head home.
No, they had to be incredibly patient.
It spent over a year just mapping the asteroid, right?
Yeah, mapping the gravity field, analyzing the surface composition. They even deployed these tiny rovers, the Minerva 2 rovers.
Which is wild. Why did they have to spend so much time just looking at it before grabbing a sample?
Well, the mapping phase was totally critical because Ryugu isn't a solid rock. It's a rubble pile asteroid.
A rubble pile?
Yeah, it's not a monolith. It's basically a loose conglomeration of rocks and dust held together by microgravity.
Oh, wow.
So if you apply too much force when you try to land or sample, you could completely destabilize the surface.
Like stepping into a ball pit.
Exactly like that.
Oh.
Or worse, you could damage the spacecraft itself. So when it came time to actually collect the sample, Hayabusa 2 performed this very delicate touch-and-go maneuver.
Right.
It descended autonomously, sensing the surface all on its own. And the moment the sampler horn made contact with the asteroid, the spacecraft fired a 5-gram tantalum bullet directly into the surface.
Wait, it shot the asteroid?
Yes, at roughly 300 meters per second.
Okay, I have to pause on that mechanism because that is just brilliant.
It's a really elegant solution to a very tricky physics problem.
Because, yeah, you can't just use a normal shovel in microgravity.
No, you can't.
If you push a shovel into the ground, basic Newtonian physics, the equal and opposite reaction just pushes your spacecraft right back up into space.
Exactly. You just launch yourself backward.
So by firing that tantalum bullet, they transferred all that kinetic energy into the regolith, basically kicking up a plume of subsurface dust and pebbles.
And those pebbles were then caught right in the sampler horn as the spacecraft immediately fired its thrusters to back away.
That is so incredibly cool.
It is, and they actually performed this operation twice.
Really? I didn't realize they did it twice.
Yeah. The second time, they did it near an artificial crater that they had created earlier using a much larger kinetic impactor.
Oh, so they blasted a hole first to get underneath the surface.
Precisely. That allowed them to access completely pristine subsurface material that hadn't been heavily altered by solar wind or cosmic ray, weathering over billions of years.
Unbelievable.
Yeah.
So after all of that, the 2014 launch, the years of transit, the mapping, firing space bullets, Hayabusa 2 begins the long journey back. And it finally drops its re-entry capsule into the Earth's atmosphere in late 2020.
Landing right in the Australian outback.
Yeah, the Woomera test range. And when the curation team in Japan finally got their hands on it and they opened the sample container, the total yield across all of those crazy operations was 5.4 grams of material.
Yeah, a remarkably small mass.
Less than a fifth of an ounce.
It's roughly the weight of a single sheet of paper.
Okay, so I know there is an immediate question that comes to mind for you listening at home, and I'm going to play the skeptic for a second here.
Go for it.
Wait, a 6-year, multi-billion-dollar mission, a 300 million kilometer round trip utilizing ion propulsion and kinetic impactors, all for 5.4 grams of black dust.
It sounds a bit underwhelming when you frame it like that.
Right, because we already have thousands of meteorites sitting in museums and laboratories all around the world. Why not just study those? Why is that minuscule amount of asteroid dirt so invaluable?
That is the big question. And it all comes down to a very strict requirement in astrobiology, which is avoiding terrestrial contamination.
Contamination from Earth.
Exactly. Think about what happens when a normal meteorite enters Earth's atmosphere. Its exterior is subjected to extreme thermal ablation. It gets incredibly hot.
Burning up like a shooting star.
Right. And then it impacts the ground. Now, our planet is absolutely teeming with a biosphere that is incredibly aggressive.
We have biology everywhere.
Everywhere. The very second a carbonaceous chondrite hits soil or ice, it absorbs Earth's water. It is instantly colonized by terrestrial microbes, and its chemical isotopic signature is completely compromised.
Oh, so it just immediately soaks up Earth life.
Yes. So when we analyze a meteorite that fell to Earth naturally, and we find amino acids or nucleobases in it, there's always this rigorous, often tedious burden of proving that those organic molecules aren't just Earth's biology hitching a ride on a space rock.
Oh, I see. You have to prove it's actually an alien molecule and not just some soil bacteria that crawled inside.
Exactly. And that is incredibly hard to do definitively.
So the 5.4 grams from Ryugu, they are basically the ultimate control group.
Precisely. They are a perfectly uncontaminated time capsule representing the early solar system from roughly 4.5 billion years ago.
Wow, 4.5 billion years.
And you have to remember, the sample container was designed to seal perfectly in the absolute vacuum of space.
So no air got in during the flight back.
Right. When it was recovered in Australia, it was immediately placed inside a specialized gas-purged clean chamber before being transported to the curation center in Japan.
So it never even touched Earth air.
Never. It was opened in a vacuum environment and then handled strictly in pristine nitrogen. No oxygen, no terrestrial moisture, and certainly no microbes ever touched that 5.4 grams.
Which means any complex organic chemistry we find inside that rock
is undeniably extraterrestrial in origin.
Oh, okay, that makes sense. The lengths they went to for this purity are just staggering.
Which brings us, I think, from the macro engineering of the retrieval to the microscopic chemical revelation.
The fun stuff. Right. Because for the first few years after they opened it, the analysis of the Ryugu samples yielded some really fascinating, but I guess somewhat expected, results.
Yeah, for a carbon-rich asteroid, they found what they thought they'd find. Various organic molecules, some basic amino acids.
But the narrative shifted dramatically when the focus narrowed to the specific nitrogenous bases.
Yes, the scientific community had been incrementally building to this realization. Because back in 2023, researchers using some incredibly high-tech, ultra-high-resolution mass spectrometry, they announced they had identified uracil in the Ryugu samples.
Uracil.
Right, uracil is a pyrimidine. It's a single ring structure, and it's one of the 4 nucleobases that actually constitute RNA.
Okay, so finding a clear, uncontaminated pyrimidine in space rock, that was a landmark validation of prebiotic synthesis models.
It was huge news on its own.
But finding just uracil is sort of like finding a single letter of an alphabet, right?
Exactly.
I mean, it proves the ink and the paper exist, but it definitely doesn't give you the vocabulary to write a book.
Right, it's just one piece of a very complex puzzle.
That is why the more recent findings, led by a team from the Japan Agency for Marine Earth Science and Technology, or JAMSTEC for short, are so profound.
Yeah, they really blew the doors off this thing.
Because they didn't just find uracil, they recently confirmed the presence of all the canonical nucleobases.
All of them.
Adenine, guanine, cytosine, thymine, and uracil. All of them in a single rock from space.
The complete suite. And honestly, it is difficult to overstate how thermodynamically surprising this actually is.
Walk us through the biology 101 of this. Why is it so surprising?
Well, we are talking about both purines and pyrimidines here. Purines, which are adenine and guanine, are double ring structures containing carbon and nitrogen.
Okay, double rings.
And then pyrimidines, which are cytosine, thymine, and uracil, those are single ring structures. Now, in terrestrial biology, here on Earth, these bases pair up to form the actual rungs of the DNA double helix.
Right, the famous ladder structure.
Or they form the structure of single-stranded RNA. To find all of them coexisting within the matrix of a single primitive space rock.
Right.
It suggests a level of chemical complexity in the early solar nebula that just far exceeds all of our baseline models.
If we use an analogy here to really make it accessible, if DNA, that famous double helix, is the master genetic blueprint locked safely in the architect's office.
I like this analogy.
Right. Is single-strand RNA basically the project manager running out to the construction site to actually implement those instructions?
That is a fantastic way to put it. DNA holds the information, and RNA translates it into action, into actual proteins.
And so finding both the blueprint pieces, the DNA bases, and the messenger pieces, the RNA bases, in a single space rock is just staggering.
It really is.
But wait, I want to push back on the thermodynamics here for a second. You mentioned how surprising this is chemically.
Yeah, it takes a lot of energy to form these bonds.
Right. If the vacuum of space is near absolute zero, and these chemical structures, especially those double-ring purines you mentioned, if they require energy to form bonds between carbon and nitrogen, where on Earth is the activation energy coming from?
That's a very perceptive question.
Because you can't just put carbon, nitrogen, and hydrogen in a deep freezer and expect them to spontaneously assemble into adenine, right?
No, absolutely not. And that is central to understanding asteroidal evolution. We have to differentiate between the environment of the asteroid as it is right now versus its environment 4.5 billion years ago.
Oh, so it wasn't always frozen.
Exactly. Ryugu, as we see it today, is a cold, dead rubble pile, but it is just a fragment of a much, much larger parent body.
Like a protoplanet.
Basically a planetesimal. In the early solar system, shortly after the collapse of the solar nebula, these parent planetesimals were accreting a significant amount of radioactive isotopes, primarily aluminum-26.
Okay, and as the aluminum-26 decays.
It releases heat, lots of it, radiogenic heating. Inside a parent body that might have been tens of kilometers across, this trapped heat was sufficient to actually melt trapped water ice.
So there was liquid water inside the asteroid?
Yes. So for a period of perhaps a few million years, the interior of Ryugu's parent body hosted liquid water.
That is wild to think about. A dark ocean inside a rock floating in space.
It really is. So you had this warm, aqueous environment that was rich in simple interstellar ices, things like ammonia, methanol, and hydrogen cyanide. And they were interacting with silicate minerals.
Like a giant cosmic soup.
Exactly. This aqueous alteration phase provided the necessary thermal energy and the liquid solvent environment to drive the synthesis of complex organic molecules like purines and pyrimidines.
So the oven was turned on for a few million years.
Right. And then, once the aluminum-26 was depleted and the heat ran out, the body froze solid again.
Preserving everything perfectly.
Yes, it preserved these molecules in the deep freeze for billions of years until a massive collision eventually shattered that parent body.
And the fragments from that collision sort of clumped back together to form the rubble pile we now call Ryugu.
Exactly. You got it perfectly.
That paints an incredibly vivid picture. It's not that these molecules formed in the cold vacuum at all. They were forged in a subterranean radioactive ocean inside a primordial rock, and they've just been kept in cold storage ever since.
That's the exact mechanism.
But this brings up a massive, massive point of clarification. Because if we have a rock containing liquid water, heat, and the complete nucleobase inventory for DNA and RNA.
I know where you're going with this.
It is incredibly easy to make a sensationalist leap here. People hear all the bases of DNA found on an asteroid and immediately jump to the conclusion that Ryugu is harboring actual microbes.
Space aliens.
Right, space aliens. Or that life itself originated in space and just drifted here on rocks.
And we must rigorously, absolutely rigorously distinguish between prebiotic chemistry and actual biological life.
Prebiotic meaning before life?
Yes. Toshiki Koga, who is the lead author from Jamstech on this study, he explicitly clarified this point. He stated that the presence of these nucleobases, and I quote, does not mean that life existed on Ryugu.
Okay, so definitively no aliens on Ryugu.
None. Furthermore, Cesar Menor-Salvin, an astrobiologist at the University of Alcalá in Spain, he reinforced this by stating, these results do not suggest that the origin of life took place in space.
So if it's not life, then what exactly are we looking at? Just very, very lucky chemistry.
We are looking at what we call a prebiotic chemical inventory. It supports the theory of pseudopanspermia.
Pseudopanspermia. Okay, what is the difference between that and regular panspermia?
Well, panspermia is the theory that actual viable microorganisms somehow survive the journey through space and seed young planets.
Like spores traveling through the vacuum.
Right. Pseudopanspermia, on the other hand, is the theory that just the ingredients are delivered from space, but the actual assembly of those ingredients into a self-replicating organism happens on the planetary surface itself.
Oh, I see.
Because a nucleobase is not alive.
Mm-hmm.
An amino acid is not alive. They are purely abiotic organic molecules.
Right, just parts.
To use a terrestrial analogy, finding a forest full of timber and a mine full of iron ore does not mean you have found a functioning city.
That makes total sense. The components are there, but no one has built the houses yet.
Exactly. The intricate, systemic organization that's driven by evolutionary biology is totally absent on the asteroid.
But having the lumber delivered is still a huge deal for the early Earth, right?
A massive deal. Because early Earth was a highly volcanic, chaotic environment. The organic synthesis required to produce these very delicate molecules from scratch might have been incredibly difficult to sustain on the surface.
Because the lava would just destroy everything.
Right. But if millions of asteroids like Ryugu were bombarding early Earth, they basically acted as cosmic delivery vehicles.
Seeding the primitive oceans.
Yes. Seeding the oceans with the pre-assembled chemical vocabulary required for life to eventually emerge.
I want to challenge the mechanics of that delivery vehicle concept, though.
Okay, what's the hang-up?
Well, we talked earlier about how modern meteorites are subjected to extreme thermal ablation when they enter Earth's atmosphere. We said they basically burn up.
Yes, they do.
So if these asteroids are hitting the Earth at, 15 to 20 kilometers per second?
Easily that fast, sometimes faster.
But kinetic energy converted to heat is just astronomical. Wouldn't the sheer thermal shock of an asteroid impact completely incinerate these delicate pyrimidine rings before they could ever seed a primordial ocean?
It definitely seems intuitive that they would be destroyed, right? But the physics of atmospheric entry actually offer a surprising protective mechanism.
Oh, really? How does that work?
It is often referred to in astrobiology as the baked Alaska effect.
Baked Alaska. Like the dessert.
Exactly like the dessert. Think about how a baked Alaska works. You put ice cream in an extremely hot oven, but the meringue on the outside insulates it so the inside stays frozen.
Right.
When a space rock hurtles through the atmosphere, the extreme friction heats the exterior to thousands of degrees, causing it to melt and ablate away.
That's the shooting star we see.
Exactly. However, solid rock is actually a very poor conductor of heat, and the entire entry process only takes a few seconds.
Ah, so it happens too fast for the heat to soak in.
Right. The exterior vaporizes, but the thermal pulse simply doesn't have time to penetrate deeply into the interior of the rock.
Wow.
So if the parent asteroid or the incoming meteorite is large enough, Its core remains at the freezing temperature of deep space, even as the outside is burning, and even as it impacts the ground.
So the outer shell basically sacrifices itself to protect the frozen, organic, rich payload inside.
That's beautifully put, yes. And upon impact, the rock fractures, finally exposing that pristine, still frozen interior to liquid water of the early Earth.
That is incredible. So over millions of years of heavy bombardment, enormous quantities of extraterrestrial organics were successfully transferred down to the terrestrial biosphere without getting burned up.
Safely delivered.
Now, if the pseudo-panspermia model is correct, Ryugu cannot be an isolated anomaly. I mean, if early Earth was seeded by this mechanism, it requires a solar system-wide distribution of these materials. We really can't base a universal model on 5.4 grams of a single asteroid. We need comparative data.
Absolutely. Good science demands comparative data.
Right.
And fortunately, the comparative data strongly supports this model. Ryugu is not our only pristine sample anymore.
Oh, right. Because just last year, NASA's OSIRIS-REx mission returned material from another near-Earth asteroid, Bennu.
Yes, Bennu. Now, Bennu is a B-type asteroid, which means it's slightly different in its spectroscopic signature than Ryugu, but it's still a primitive carbonaceous body.
And did they find the same things?
They did. The preliminary analysis of the Bennu samples absolutely confirms the presence of the exact same fundamental building blocks.
Which provides an immense level of validation.
It really does. But we can also look back at the meteorites we already have on Earth, too.
Wait, really? But we spent so much time earlier talking about how terrestrial meteorites are contaminated by Earth life.
They are. But despite the contamination issues, chemists have developed incredibly sophisticated ways to differentiate between earthly biology and extraterrestrial chemistry within those fallen rocks over the last few decades.
Okay, so how do you tell the difference between alien uracil and Earth uracil?
Well, the most famous example comes from the Murchison meteorite, which fell in Victoria, Australia, back in 1969.
1969, same year as the moon landing.
Exactly. It was a massive fall of carbonaceous chondrite material. When scientists initially analyzed it and found amino acids inside, there was massive skepticism.
Because everyone just assumed it was dope from Australia.
Right. The assumption was that it must be terrestrial contamination. But then chemists looked at the chirality of the amino acids.
The chirality? What is that?
It means handedness. Some molecules are asymmetrical, meaning they come in two forms that are mirror images of each other, like a left glove and a right glove.
Oh.
Now, for reasons we still don't fully understand, terrestrial biology almost exclusively uses left-handed amino acids. Every living thing on Earth relies on the left-handed version.
Interesting.
But the Murchison meteorite contained a near-equal mixture of left and right-handed amino acids.
A 50-50 split.
Yes, what we call a racemic mixture. And a racemic mixture is a hallmark of abiotic chemical synthesis. It means it formed through random chemical reactions, not biology.
Because biology is picky and only uses one hand, but random chemistry makes both equally.
You got it.
Furthermore, they can look at the isotopic ratios, right? Like carbon-13 versus carbon-12.
Precisely. Extraterrestrial organic molecules often have a distinct, heavier isotopic signature. They have higher ratios of carbon-13 or deuterium compared to standard terrestrial organics.
So by checking the weight of the atoms, basically you can tell where it came from.
Right. By analyzing the Murchison meteorite and also the Orgau meteorite, which fell in France in 1864.
Wow, 1864.
Yeah, a long time ago. But by isolating those heavy isotopic signatures, scientists were able to confirm the presence of extraterrestrial nucleobases long before Hayabusa 2 ever launched.
Okay, so we have this historical baseline from Murchison and Orgau, and now we have perfectly pristine, uncontaminated control data from Ryugu and Bennu.
Exactly.
I think Cesar Menor-Salvin pointed out that by comparing Ryugu and Bennu, we now possess a definitive empirical understanding of which organic materials form under prebiotic conditions universally.
Yes, it essentially removes the speculation from the field.
Right. We aren't just guessing what could theoretically happen in a nebula anymore. We hold the physical proof that this chemical starter kit is basically standard issue across the solar system.
Think about that next time you look up at the stars. The universality of this chemistry is profound.
And here's where we get to the real plot twist. What the researchers did next elevated the study from just a really good confirmation of existing theories to the discovery of an entirely new chemical paradigm.
Yeah, this is where the paper gets really exciting. Because they didn't just catalog the presence of these nucleobases and say, hey, they're here.
Right.
They meticulously quantified the concentrations of each individual molecule across all the different asteroidal samples.
They counted them.
Yes. They compared the specific ratios of purines to pyrimidines in Ryugu, Bennu, and Murchison.
Because logically, if the chemistry is universal, you would expect the ratios to be relatively consistent, right?
Yeah.
Assuming they all formed from the exact same primordial cloud of gas and dust.
Exactly, that was the assumption. But they found significant variations.
How significant?
Very. The quantities and the relative abundances of the nucleobases varied wildly depending on the specific parent body they were looking at.
Oh, wow.
This indicates that while the base ingredients are universal across the solar system, the chemical evolutions, the specific pathways driving the synthesis, is actually highly sensitive to the local conditions of the asteroid itself.
So every asteroid is baking a slightly different version of the same recipe.
Exactly. The thermal history, the degree of that aqueous alteration we talked about, the exposure to cosmic rays over time. These variables act as a highly localized chemical engine.
And here's where it gets really, really interesting. Because the data reveals a massive, glaring mystery about how that chemical engine actually works.
The ammonia anomaly.
Yes. The Japanese team mapped out the varying concentrations of the DNA and RNA building blocks, and then they cross-referenced that data with the concentrations of other volatile chemicals trapped in the rock. And they identified a direct, unmistakable correlation between the abundance of nucleobases and the concentration of one specific chemical, ammonia.
This is truly the inflection point of the entire study. They observed that as the concentration of ammonia fluctuated across the different samples, the production and preservation of the nucleobases shifted in direct correlation.
They matched perfectly.
Right. Ammonia, which is structurally NH3, is clearly serving as the primary nitrogen donor in these reactions.
But when Toshiki Koga analyzed the specific correlation, he stated flatly that, quote, no known formation mechanism predicts such a relationship.
Which is an incredibly jarring statement coming from a lead astrobiologist.
Right. I mean, we have been modeling prebiotic chemistry for decades, haven't we? Running endless computer simulations of how ammonia interacts with carbon compounds in deep space.
Decades of work, yes.
And yet, our current science basically has zero explanation for why ammonia and nucleobases are scaling together in this exact manner on these asteroids.
It highlights a fundamental gap in our understanding of interstellar chemistry.
Yeah, so?
Well, when we normally model the synthesis of complex organics, we typically look at classical pathways like the Strecker synthesis. That's where aldehydes react with ammonia and hydrogen cyanide to form amino acids.
It's okay.
We also look at Fischer-Tropsch type reactions, where carbon monoxide and hydrogen react over a metal catalyst like iron or nickel found in the dust to form hydrocarbons and more complex rings.
So we know the basic mechanisms, and we know ammonia is crucial.
Yes. It provides the nitrogen necessary to build the purine and pyrimidine rings.
So if we know ammonia is the nitrogen donor, why is the correlation baffling?
Because the rate and the ratio of the synthesis that we are observing in the Ryugu samples do not align at all with the thermodynamic yields predicted by those classical pathways.
Wait, let me make sure I get this. The math doesn't add up.
Exactly. In our laboratory simulations, if we introduce a specific amount of ammonia, it yields a predictable, relatively low concentration of nucleobases under simulated asteroidal conditions.
But the Ryugu samples have way more than they should.
Right. The physical evidence from Ryugu suggests a shadow mechanism.
A shadow mechanism.
A highly efficient, completely unrecognized chemical pathway where ammonia acts not just as a reactant, but perhaps as a catalyst or some kind of stabilizing agent in a way we simply haven't mapped yet.
Wait, I have an idea. Could the ammonia be acting as an antifreeze during that radiogenic heating phase we talked about earlier?
Oh, that's a very good thought.
Because if the parent body had liquid water, ammonia would lower the freezing point of that water significantly, right? Like salting a road.
That is a highly plausible physical mechanism, actually. An ammonia water solution can remain liquid at temperatures far, far below the standard freezing point of pure water.
So it stays slushy for much longer.
Exactly. This would significantly extend the duration of the aqueous alteration phase inside the parent asteroid. So instead of the liquid phase lasting 1 million years, an ammonia-rich brine might remain liquid for tens of millions of years.
Which provides a vastly extended time frame for the slow, methodical synthesis of all these complex nucleobases.
Right. It gives the oven way more time to bake the cake.
But Koga's statement implies it's actually more than just extending the liquid phase, right? The chemical correlation itself is unpredicted.
Yes. It's as if we thought we knew the recipe, but we're finding out there's a secret enzyme or some pressure variable that we just entirely missed.
Morgan Cable, a scientist at the Victoria University of Wellington who reviewed this research, she actually noted that this ammonia finding is unique and has major implications for how biologically important molecules originally formed.
And she's absolutely right, because if there is a highly efficient, unrecognized pathway utilizing ammonia to forge nucleobases, it fundamentally rewrites our understanding of how easily life's precursor materials can be manufactured in space.
It makes it seem a lot easier than we thought.
Exactly. It significantly lowers the thermodynamic barrier.
It basically means the universe is far more proficient at generating the alphabet of biology than we gave it credit for. I mean, if this shadow mechanism is utilizing ammonia in a highly efficient manner, it suggests that the chemical starter kit for life isn't a rare bottleneck at all.
Right. It is an inevitable consequence of basic cosmic chemistry.
That is such a profound shift in perspective.
It completely reinforces the concept that the universe is inherently predisposed toward complexity. We started with the assumption for decades that life requires rare, mathematically perfect conditions to even get the ingredients right.
The Goldilocks zone for chemistry.
Yeah. But if simple ices like ammonia and carbon monoxide, subjected to just the standard radiogenic heat of a primitive space rock, inevitably cascade into the complete suite of canonical nucleobases.
Through robust, unrecognized pathways.
Exactly. Then the threshold for prebiotic synthesis is just remarkably low.
Okay, let's synthesize the immense scope of what this all actually means for you, the listener.
Let's do it.
We began with a spacecraft intercepting a 900-meter rock 300 million kilometers away. We retrieved 5.4 grams of pristine carbonaceous chondrite, shielding it entirely from Earth's aggressive biosphere.
A monumental feat of engineering.
And within that microscopic pinch of black dust, high-resolution mass spectrometry revealed not just simple organic molecules, but the precise, complete 5-letter alphabet of DNA and RNA.
Adenine, guanine, cytosine, thymine, and uracil.
We established that the thermal shock of atmospheric entry actually protects these delicate structures inside a freezing core, allowing asteroids to act as cosmic delivery vehicles.
The Bait-Alaska effect.
Seeding the early Earth with the exact vocabulary required for biology to take hold.
And, crucially, as we just discussed, we discovered that the engine driving this incredible synthesis is tied to a correlation with ammonia that completely defies our current chemical models.
Which I love. It shows we still have so much to learn.
It really highlights the absolute necessity of physical sample return missions. You simply cannot discover an unrecognized chemical pathway by just pointing a telescope at the sky or running another computer simulation.
You have to get your hands dirty.
You do. It requires holding the primordial material right there in a laboratory and observing the empirical reality of how the universe builds complexity.
It takes the collective scientific apparatus of humanity just to trace the lineage of a single cell back to the dust of the solar nebula.
Which is a beautiful way to look at it. The integration of aerospace engineering, orbital mechanics, analytical chemistry, and astrobiology all working together to decipher a single truth about our origins.
And I think that leaves us with a truly profound, lingering concept to consider as we wrap up.
What's that?
Well, we now hold the physical proof that the exact organic materials required for biology form universally under prebiotic conditions, driven by these highly efficient ammonia pathways. We know definitively that carbonaceous asteroids act as preserved laboratories, just flying around our sun carrying this complete chemical alphabet.
That's a fact now.
So if the laws of chemistry and thermodynamics are uniform across the cosmos, what do you think is currently trapped in the ice and rock of the billions of pristine, untouched asteroids orbiting the other stars in our galaxy?
Just waiting in the cold dark.
Exactly, just waiting to crash into a young, warm planet.